I want to cover the last few slides that aren't math related in Unit 1. So I want to talk about derived units. Derived units essentially are units that were plugged into an equation to get the final unit. So speed is distance divided by time. So we have meters per second or feet per second. Like, it doesn't matter which, but you get the idea. It's something over something. Now, area, though, if you want to find the area of something, you would just do length times length. So if I have a meter times a meter, I get meters squared. If I have a centimeter times a centimeter, I have centimeters squared. So that is also considered to be a derived unit. Volume. In general, this is not for all shapes, right? But in general, volume is length times width times height. Actually, so that shouldn't even be that, but length times width times height. So again, if I take a centimeter times a centimeter times a centimeter, that would be centimeter cubed. Again, there are other formulas for spheres, for cylinders, but again, even if I put the equation up here, you would still end up with something cubed in the formula. You have to think about its formula, but I guarantee it's going to come out as a cubed. So any length unit cubed is volume. That's the easy way to say it. Any length unit cubed is volume. But you also have liters and milliliters. So this fact you'll need to know. 1 milliliter is equal to 1 centimeter cubed. It's one of those basic facts that'll apply in density, which we'll talk about in a second, but you need to know that. Density is also a derived unit, which is mass over volume. So again, mass, most likely in this class, we're going to deal with grams and not really kilograms. Volume could be milliliters or it could be centimeter cubed. So that's why you see both options for density. If you Google a density for a substance, you might see different units posted for the density. So it just depends how they were measured, which again, we'll talk about. So again, density is a ratio of mass to volume. It is equal to mass over volume. It is a physical property. It stays the same for a set substance. If you're curious, you can look at page 36 in your book, and there are examples of published densities. So, how do we measure mass? Easy. We use a balance, and we'll get grams. How do we measure volume? Well, it kind of depends. Milliliters, as was mentioned on the previous slide, is going to come from a graduated cylinder, which again, I'll show you in class. But if I'm using a ruler on a cube, I'm going to do a centimeter times a centimeter times a centimeter, and it's going to be centimeter cubed. Or if I have a box, again, it would be centimeter times a centimeter times a centimeter. So again, that's why it could be either grams over milliliters or grams over centimeters cubed. Observations in this class. We're going to do lots of labs. You're going to be observing things. So quantitative sounds like the word quantity, right? So if I have a quantity of something, I have a number. So quantitative observations are going to have numbers, whether it's a mass, whether it's a volume, whether it's a temperature, you get the idea. Qualitative sounds like the word quality. So essentially, you're just describing, is it shiny? Is it black? Is it big? Is it, I'm running out of words right now, but you get the idea. So I just wanted to point that out. The last words, vocab words, I want you to know are precision versus accuracy. People quite often mix these two words up. Accuracy is how close a measurement is to the actual value. So if the object weighs 4 grams, and that's its actual, and your balance is, you think, working, but you get a mass of 3.5 grams. Well, that's not very accurate, right? So that's what accuracy is. When you take a test, you are trying to be accurate, right? You want to get the answer right. Precision, on the other hand, this is where people mix up the word. Precision is when you make several measurements, and are they close to each other? So this balance that is broken, we get 3.5 grams the one time, then we get 3.45 grams the next time, then we get 3.55 grams the next time. All three of those numbers are pretty close together, right? But they're not accurate. So precision is how close they are to each other. There are many kind of errors that can happen in chemistry, and part of being a good chemist is being able to do an error analysis to realize where your errors are and how they could have affected your results. So random errors, unfortunately, are ones that kind of can't be explained, and they're going to give you inconsistent numbers. Systematic errors are ones that are something's happening every time and it's just giving you consistent wrong numbers. So again, back to this balance. It needs to be calibrated. Something's off. It's not measuring correctly. So that's a systematic error. I always use the bullseye as a visual for these two words. In this first bullseye up here, you can see all the arrows are in a cluster and they're at the bullseye. So they are very high with accuracy and very high with precision. On the bullseye over here, you can see they're clustered off to the side. The one here at the bottom, they're all around the bullseye, but they're not in the bullseye. So they are accurate that they're around the bullseye, but they're not very precise. This one doesn't happen very often, so I really wouldn't worry about this example as much. But this one could happen where they're just all over the place. You don't have precision and you don't have accuracy, and it's not good. So, with that idea, you're going to have to be able to calculate percent errors. Oh, I totally messed up. This should be here. So I'm going to erase that. Okay, so percent error is defined as experimental minus actual divided by actual, and then you multiply by 100 when you're done that. Now, what do these bars mean? Do you remember that from math class? That means absolute value. So essentially, it doesn't really matter if you do actual minus experimental or experimental minus actual, because you're just going to make the number positive. But what does matter is that you divide it by the actual number. So in my class, it kind of depends on your professor, it depends on your teacher that you have in life. They might want you to take away the absolute value bar. And if you get a negative number, the actual value is more than the experimental. Now, I didn't even cover what these words mean. Experimental, because it has the word experiment in it, is the one you got from your lab. The actual value is what it should actually be. So it doesn't really, in my mind, matter if it's positive or negative. It's just telling you how far you are from the actual, and it puts it into a percent. Percents are always based out of 100, right? So this will be much better explained through some examples in your packet, but I just want to put the definition up there of what percent error is. So that should cover all the content in the chapter. Now we just need to practice stuff in your packet.